All right, we're going to cover polarity. And so we have to talk about polarity a little. Um, and so when we talk about polarity, we actually talk about bond polarity in this first one. So if you remember, like if you had something greater than 1.7 in terms of electronegativity, that was ionic, right? And then if it was less than 1.7, specifically if you had 1.7 to 0.3, remember these are differences in electronegativity. It would be covalent, but it would be called polar covalent. And then 0.3 to 0 is nonpolar covalent. So what does that mean? So we're going to focus on this part here since we're doing covalent bonds. But what does that mean specifically? So if we look at nitrogen and fluorine, so nitrogen is here. Oops. And fluorine, let me do it in a different color. So nitrogen is here, and fluorine is here. So if I were to draw out nitrogen being bonded to fluorine, I'm not going to worry about, how many bonds and that kind of stuff. I'm just putting nitrogen with fluorine here. Let's just imagine that's one of the bonds. Nitrogen has an electronegativity that is 3.0, right? And fluorine has 4.0. So first of all, the difference is 1.0. So this is a polar covalent. But what does that mean? Well, if you remember, polar means they're sharing unequally. Fluorine is stronger, has a greater electronegativity. So what that means is the pair of electrons that is shared between nitrogen and fluorine isn't shared equally. It's actually shared unequally. So it doesn't look like this. Actually, in real life, it looks more like this, right? Where fluorine actually kind of holds onto those electrons a little more tightly, just because it's stronger, it has a greater electronegativity. Okay. And so this is what we call polar covalent. They're still sharing the electrons, so this is still a covalent bond, but it's unshared equally because the fluorine has a stronger electronegativity. And so that's what polarity is. Because what it does is it creates a pole, right? It creates actually, so this side is what we call slightly negative. And so there's a little symbol for slightly, and this side is slightly positive. So it's not exactly all the way negative and all the way positive. So it's not as strong as ionic, but there is a slight negative and slight positive. Another way we show this is we kind of put a plus here, and then we say, hey, the electrons are kind of more that way. And so this is just saying, hey, the electrons where the arrow is pointing is more, there's more electrons on that side, or it's a little stronger. So that side's going to be slightly more negative, and the other side would be slightly more positive. So these are two ways that we show this. So if we look at chlorine and a bond between chlorine and nitrogen, you'll see that they actually are both 3.0. So those electrons are actually going to be right in the middle, being shared equally. So there's no polarity. It's nonpolar. There's no pole. There's no negative pole and positive pole. It's just straight down the middle. Okay. So just want to remind you that when we have polarity, we kind of use these symbols here just to show that there's a slight negative and a slight positive. But what we really kind of want to focus on, though, is what we call molecular polarity. And so in this case, we kind of look at the whole molecule and then kind of decide if it has polarity or not. Remember, polarity just means that like one side is slightly more positive, one side is slightly more negative. So here we have so CF4. So just to show you, 4 plus 7 times 4, 28 is going to give you 32. So this is just going to be straight like this. Okay, so if we look at the specific bond polarity, like let's just look at one bond. Let's just say this one here. Carbon is 2.5 and fluorine is 4. So Fluorine's more electronegative, so this bond is polar in this direction, if that makes sense, right? Just kind of we had that. But if we did it to all of them, you would see that like they're kind of opposites. So there's kind of a symmetry to this, right? Where, although you have polarity going in this direction, the opposite is true. You have an equal polarity going that direction. So in general, this total molecule is nonpolar. So it's a little strange because each bond is polar, right? Each bond has polarity. But because you have symmetrical kind of things working against each other, the whole molecule altogether is going to be nonpolar. So let's look at another example and see if that helps. So let's look at NH3. So let's just draw NH3. So NH3 looks like this. So if you look at it, NH3 is a little strange because the nitrogen is a little more electronegative. So you have hydrogen, which is 2.1, kind of going this way, that way. Let me do it in different colors, sorry, so it's easier to see. And so actually what you see is like there's symmetry here, right? Like they're kind of, pushing against each other. But if in this direction, this up and down direction, it doesn't really work, right? Because there's nothing like against it over on this side. So this would actually be polar. Okay. Because there's an uneven charge. So if we were looking at it, the more positive side would be like over here. We would actually draw it like this. And then the more negative side would be up here. Okay. Because the horizontal ones, like these ones here, cancel out. But this one here is kind of pushing it over here. And so it's a little more, slightly more negative. Now, a couple things that I need you to know. Like, you don't actually need to show me all this stuff here. Like, if you can look at this structure and be like, oh, that's going to be polar. Because you can see that it's not, like, symmetrical, if that makes sense. So if you can see that, like, that's all you need to do. I mean, you don't need to draw all this stuff out. I'm just showing how it works. And so let me show you the next one. So if I show you this, you can almost see like they all have, kind of equivalent parts here. And so this is nonpolar. Okay. And because remember, you have this going on here, but they kind of cancel each other out. These here kind of cancel each other out. So this is nonpolar. So hopefully you can kind of see like, hey, this one is polar, whereas the other one is nonpolar. So this is polar. And you can kind of see the lack of symmetry here causing the polarity, where you have some kind of symmetry there. So kind of interesting question. See if you can figure this out. But this one is kind of tricky. But let's say I had say BF3. So remember, BF3 is one of those ones that it's one of those ones that it's a little different. Remember, because so what do you guys think this would be? Do you think it would be polar or non-polar? So this one would actually, it's a little strange, but they're all kind of pulling equally at the correct angle. So if later in physics you learn about these vectors, but This at pulling an angle is pulling in this direction, but also pulling in this direction. And then this angle is pulling in this direction, but also that direction as well, like this diagonal force. So since there's some symmetry here going on, this is actually nonpolar. Okay. All right. Hopefully that helps. There will be a worksheet to kind of accompany this, so you can kind of get some practice on it. Okay.